It always does that. That was on mute. Good morning, everybody. So I've got the key up here to the assignment. So if you need to check your answers, please do so. You're going to see some odds, even though it was only evens. You're going to see some odds from a previous assignment. So don't worry more about that. Scrolling down here, just pause where you need to. You see the evens along the right side. There's 18, 20, and 22. So 18 is a factor. Remember that it is a factor when it goes all the way to 0, right? I can't really see it on the TV up there, but on this board you see the remainder ends up being 0. Don't forget to put in the zeros. It's a very common mistake when you're synthetically dividing. Crazy enough, you know what one of the math sections was on last night's academic challenge match? Synthetic division. Well, you could choose to do either long division or synthetic division. So given this polynomial divided by this linear binomial. Scrolling down here, did anybody study 20 up top? No? Okay. We go down here for 22, 24, and 26. Yeah. So this is one of those some are different with cubes one, right? We got 125 plus z to the third. 125 plus z to the third. Okay, so if it's a two-term, you know, there's no GCF, obviously, but if it's a two-term, it's got to be either difference of squares, difference of cubes, or sum of cubes. These aren't perfect squares, so I disregard the difference of squares, and it's a plus sign anyway. So the only thing it could possibly be to factor down is the sum of cubes. Let's see, is z to the third a perfect cube? Yes, the power is divisible by 3. Is 125 a perfect cube? I recognize that one is 5 to the third, but if you needed to do it in your calculator, you could actually write third root of 125. You could actually type that in your calculator and see, yes, that is indeed 5. So what do? So now that we see that it is, these are perfect cubes, what I can do here is I make my binomial and a trinomial. I like to write in the signs first. Remember, it's same, opposite, always positive. Same sign, opposite sign, always positive. And then we cube root for our binomial. Okay, so that means I've got a 5 here and a z here. And then I take squared product squared. Squared, product of the two, squared. Now, this is a completely fine answer. You may have switched it around, though, and that would be completely fine. And that's what you see on the key here. To put it into standard form, that would be completely fine, but you don't need to do that. A lot of people ask, do we need to try to factor down more? You should always try to factor down to make sure. But I'll tell you right now that there's no factors of 25 that equal -5, so you don't have to worry about that. And it's never going to factor down. Just a kind of spoiler alert on that one. Anything of the form a squared minus ab plus b squared is never going to factor down. It's never going to happen. Okay, so you can kind of stop there. Does that answer your question? So I got the work for 26 on the board still. Here's 28 and 30 then on the right side. Number 27, even though you did not have to do that one, that's a really interesting problem. Here's why. Take a look at what we've got there. It's s to the 6th minus 1. Yes, 1 is a perfect cube. 1 times 1 times 1. S to the 6th is a perfect cube, so it's s squared times s squared times s squared. It's 6 divided by 3 is 2. Okay, so that means that this does exist. This is a difference of cubes. So I say, okay, I've got binomial and a trinomial. And so we take same, opposite, always positive for the signs. The cube root of s to the 6th is s squared. 6 divided by 3 is 2, s squared. The cube root of 1 is 1. And then we take squared product squared. And that's what you see here. S to the 4th, S squared, 1. Now, the only catch is, and this should be in parentheses here, over here. The only catch is that this S squared minus 1 is another difference of squares. You can make that S minus 1, S plus 1. Okay? That can sometimes factor down. Okay? That can sometimes factor down. The trinomial is never going to factor down, but the binomial may, if it turns out to be one of those special cases where it turns into a difference of squares. Okay, let's keep scrolling it down a little bit. Here is 32 and 34 and 36. Yeah. Yeah. Let me get the original problem out of the book here. Just jump over here. What page is this on? 433? Ooh, went too far. Demo. Come back down. Oh. 433. Well, come on, I want to screen capture thing. What problem is that again? 32? Okay. Whenever you take a screen capture, it like shows like a picture sound. That's really weird, I know. All right, here's 32. Let's ask where my markers were. There it is. The volume of a bowling ball can be modeled by the function v of x is equal to 168 minus 28x squared minus 28x minus 28x squared. Okay, so where x represents the radius of the finger holes. Identify the values of x for which v of x is equal to 0 and use the graph to factor. All right, so we see this quadratic here, right? It's x squared, so it's generally going to be looking like this function. And it will have another 0 over on this side, but in the negative. Where is the 0 that we see from the graph? Where's it at? It's a 2. Right? We see that there is a 0, and a 0 exists at 2. So what we can do here to use the graph to factor it down is take 2 in the box and synthetically divide. Now make sure you put this into standard form, negative 28x squared minus 28x plus 168. And you know what I could do? Because if I really want it, well, I'll just do it with 2 real quick. Hold on. Negative 28, 168. And negative 28, negative 56, 28 plus 56. That's early. 84. Oh, duh, we knew that. Because this is going to turn into negative 168 and be a 0. Right? Okay, well, that means that I have x. Remember that this x equals 2 corresponds to a factor of x minus 2. And then this leftover piece, negative 28x minus 84, can factor down, right? Because it's got a GCF. It at least has a GCF of a, I can factor out a negative. But what's my biggest factor that I can take out of 28 and 84? Is it 7? I think it's 7. 28 divided by 7 is 4. 84 divided by 7? 12. It's something even more than. Is it 14? 84 divided by 14? Yeah, it is. Is it all 28? Is 84 divisible by 28? Well, isn't that something? So we can actually take the whole 28 out. Negative 28. And then we've got an x minus 2. I like to put it all the way in front. And so that would leave an x plus, what was it, 3? Yeah. unpin it from the computer. X plus 3. And that's how we use the graph to factor it down. Okay? That's it in fully factored form. I want to see what the book did. Because what I actually thought of doing first was taking out the GCF first. But it said to use the graph to factor down, so I'm thinking they would want us to do the 2 first. But, you know, let's see what they did. They did a -3 first. Did they get the negative? You see the 2 from the... Whatever. Same answer. That's weird. Number 36 is a fun problem. Okay, because that one does factor by grouping. And then you see a difference of squares and a sum of cubes in it. Which is pretty cool. All right, any other questions? Anything on that? We're going to spend 2 days on section 6.5, and then we're actually going to do a review day on Thursday. Now, how many of you guys are signed up to take the AccuPlacer on Thursday? Okay, it's like a lot of my 7th period class, too. Which 3 people is a lot of this. But anyway, that being said, don't forget that you can still, I think you can still sign up for the AccuPlacer on Thursday. I know it's Tuesday right now, but I think you can. I think the link is still live. You can at least try to. But if you have not already done so, if you haven't gotten the score from the ACT to do CCP pre-calc, you want to take the AccuPlacer to try to get the score to take CCP pre-calc. Unless you know you're just going to take regular pre-calc, then that's fine too. But if you want to take CCP pre-calc, you need to either have the 22 on the ACT or these qualifying scores on the AccuPlacer. What's unique about Thursday is that Thursday they're offering it in school. Remember, they're offering the AccuPlacer in school. So if you'd like to sign up for that, that's on the counseling website.
I didn't get you. Can I?
Oh yeah.
You blocked the number. All right, I got it.
So it's on the counseling website. So you just go on there, you click College Credit Plus, and you sign up on there. The test is Thursday for the in-school, and then next, like in February, there's one after school. So you could take both if you wanted to. Like if you don't get the qualifying score on this one, you can take both. But it is during the school day on Thursday. Have they told you guys when you're taking it? Okay, because we had a discussion about that 7th period, and they had not yet decided. The guidance office had not yet decided who's taking the test when. Because I hear there's going to be a morning session and then an afternoon session. So I'm not exactly sure when that's going to happen. And then they didn't realize that the Apex exams, the digital Apex exams, are on the exact same day. So that's fun too. Throwing a bunch of things in there. Yeah.
What do you think we should study? We should, or you think we should?
I just go in and try to take it.
Okay, I just didn't know if I was being like.
No, there's nothing really to study. I mean, if you want to try it, I think it'll be all right. Yeah. Are there practice ones on there? So you might want to just take a look at it.
Okay.
What's coming? No, one or the other.
Okay.
One or the other. Yeah. Okay. Any other questions about that? Okay, so that being said, the reason why I say that is because if you're one of the people that has to be out on Thursday, we're actually just going to take a day and I'll go over the homework and then I'll just let you guys work on the next night's homework. It's just a worksheet front and back because I'm missing people because of Apex exams. I'm missing people because of this test. So it's going to be kind of a weird day in our world. So we'll just kind of tread water for a day. Here you go. So we're going to do section 6.5 today, and tomorrow day 1 and day 2. And section 6.5 is very similar to section 6.4. Today, what we're doing is finding the roots of the polynomial. And now I hope you understand the connection of finding the roots and factoring. Right? Finding the roots and factoring. Like, to think back to quadratics, the reason we factored was to find the roots. Right? The reason we factored was to find the roots. And if you could not find the roots by factoring, you had to do another method. You had to solve by completing the square. You had to solve by the quadratic formula. Right? There must have been another way that you could have done, that you could have used to solve for the roots. Okay? So what we're doing now is in the next couple of sections, finding ways to solve for the roots. Okay? Finding ways to solve for the roots. And this is going to tie right in from yesterday, because what we're going to do today is factoring and using our graph to find the roots of polynomial equations. Now, in the last lesson that we had, we used several methods to factor these polynomials, and I kind of went through them at the beginning of class today with the flowchart. As with some quadratic equations, factoring a polynomial equation is just one way to find its real roots. Don't forget about what we have as the zero product property. If you could get it down to its factors, you could get it down to the binomials, if you will, and they're all still set equal to 0. If you can get everything set equal to 0, then you can set each piece equal to 0. That's that zero product property. Every little piece in there could possibly be 0 to make the whole thing cancel out and go to 0. Okay? So what we're going to do here is factor it down. This entire polynomial, we're going to factor it down and set each piece equal to 0. So take a look here. Here's our first example. Got 4x to the 6th plus 4x to the 5th minus 24x to the 4th. So let's start with our flowchart. Is there any GCF? What is it? 4x to the 4th. So let's remove it. That means my leftover is x squared plus x minus 6. Still all equaling 0. All right, well, we got 4x to the 4th still out front. Don't leave that behind. That's still there. And then we've got an x. Oops. Oh, thanks. You scared me a little bit there. An x plus 3 and an x minus 2. Still all equaling 0, right? X plus 3 and an x minus 2. All right, now remember the zero product property says that if I got it down to its fully factored form, I can set each piece equal to 0 on its own. I can create, I was creating like 2 little mini equations with a quadratic in our quadratics chapter, but now what we're looking at is, however many factors it has, that's how many little equations I've got. So what's going to happen with this 4x to the 4th? Well, I'll divide by 4 and I factor and I take the 4th root of it. It just turns into x equals 0. Which makes sense because anything that, any value, any variable that I pull out, any variable GCF that you have, if that gets pulled out, you're going to have a 0 root. It will run through the origin. Okay, and now we just take a look at our 2 other ones. X equals negative 3, subtracting the 3, x equals positive 2. So these are the 3 roots of this equation. Please know that there's a difference between factoring and then finding the roots. Right? There is a difference between factoring and finding the roots. You can find the roots by way of factoring. But if I just ask you to factor, like you would leave it here. And if I asked you to find the roots, you would extend it on and actually solve for x. Okay, so finding the roots or finding the zeros, you're solving for x. If I just say factor, that's where you stop here. See, I can tell you to solve, that means get x equals. I can tell you to solve by a given method. That means I get it down to its x equals. Solve by factoring, so you're going to use factoring to solve it. Don't stop at factoring. Take a look at this one here. So my first issue here is that it's not set equal to 0. So I've got to start by doing that. I've got x to the 4th minus 26x squared plus 25. Now what we're going to do here is kind of an interesting method to factoring. You notice how this is a trinomial. So maybe I might look at, maybe this is factorable like when a is 1. Right? Maybe this is that case. But the issue is I've got an x to the 4th. Oh, didn't mean to have that happen. I've got an x to the 4th, and then I've got an x squared. Usually when we have this, it's an x squared and then an x, right? Okay, so here's this little trick that we're going to learn here for these problems. Whenever you have it set up, and this is a very special case, whenever you have it set up where it's a trinomial and you've got x to the 4th and then x squared, what you could do is introduce a new variable. We're going to say, okay, we're going to let x squared equal, and then introduce a new variable. Let's say, what variable do we want to choose? A. Sure, A. Okay. We're going to introduce a new variable. And the reason we're doing this is so that we can kind of comprehend what's happening. We're going to say, let's let x squared equal a. Well, if x squared truly equals a, what is x to the 4th in terms of a? A squared. A squared. And then what is x squared again? A. Okay, now that's a little bit easier to solve. That looks a little better in our mind. So we introduce a new variable so that we can actually factor it down. Now this is a minus 25, a minus 1. But again, I created a. I need to put x back in. Okay? Well, x squared is a. So what I can do now is put x squared back in this equation. So x squared minus 25, x squared minus 1. Basically what happens is that it factors like normal, but instead of just having an x, we've got an x squared within those binomials. All right, so that means we've got an x minus 5, x plus 5, because that's a difference of squares, and an x minus 1, x plus 1, because that's also a difference of squares. And now that's fully factored down. We can set each little piece equal to 0. We can say, that x equals 5, x equals negative 5, x equals 1, x equals negative 1. And if we'd like to, we could say plus or minus 5, plus or minus 1. Understand, again, there's technically 4 roots there when I write it like that. Right? Don't forget that whenever you write it plus or minus, that's really signifying 2 places. And again, remember all the synonyms. Roots of the function are zeros of the equation, are x-intercepts of the graph. So you can think where we can head here. You know, in the long game here, we're going to be looking to see how to graph, just like we did with quadratics, finding the zeros so that we can more accurately describe the graph. Okay, next thing here. Sometimes polynomial equations, sometimes a polynomial equation has a factor that appears more than once. This creates what's called a multiple root. Take, for example, 3x to the 5th plus 18x to the 4th plus 27x to the 3rd. It has 2 what are called multiple roots. Let me show you what I mean here. If I were to factor this thing down, 3x to the 5th plus 18x to the 4th plus 27x to the 3rd, factor that down. I've got a GCF of 3x cubed to leave an x squared plus 6x plus 9. So that means I've got a 3x to the 3rd and then an x plus 3, x plus 3. Some quick factoring now. if I factor that down, I see that I've got an x equals -3 twice. It shows up twice. So that's what's called a multiple root. When the factor is present twice, it's a double root. Okay? When it's there 3 times, it's a triple root. It can have a lot of different ones. It could be an infinite amount of roots. I don't know. That seems weird. But another thing that I can say here is look at this 3x to the third. This 3x to the third, if I truly wanted to factor it down all the way, wouldn't I write this? Isn't truly, if I really expanded it all the way out, wouldn't I write it like that? And then you would say, okay, x equals 0, x equals 0, x equals 0. So whenever you have a power on an x that you've removed as a GCF, that is actually also a multiple root as well. Okay. How many times? Well, it's there, the amount of power times. So if you've got something like you removed an x to the fourth, right? Somehow, you removed the GCF of an x to the fourth, and you set that x to the fourth equal to 0. You're going to get x equals 0, but it is a multiple root. It's actually there 4 times, right? Because that would be x times x times x times x. So the root is actually there 4 times. This is what's called having a multiplicity. The multiplicity of a root is the number of times that thing is a factor. When a real root has even multiplicity, the graph is going to touch the x-axis, but not go through the x-axis. It's going to lie tangent to the x-axis. That's when it's an even root. When it's an odd root, that's when it's going to what's known as bend through. Okay, it will bend through. So this is very important here. The end game of all of this stuff is to try to graph these polynomials. These multiplicities are telling you exactly what it's going to look like if it has a multiple root at that spot. If the multiplicity of the root is odd, it's going to bend through at that point. It's going to cross through, but it's going to bend through at that point if it's an odd root. If it's an even root, it's going to be one of those ones where it just lies tangent to the x-axis, it bounces off the x-axis at that point. Okay. So taking a look here at that example that we just showed above, -3 was a double root because it was there twice. This is the graph of that function. Notice that it's bouncing off the x-axis at -3. 0 was a triple root. It was an odd root. It was there 3 times. Okay? That is going to what's known as bend through at 0, 0. Obviously, if it's a single root, I'm disregarding, when I say odd root, odd number of times. If it just has a multiplicity of 1, obviously it's just going to go straight through. That's it, right? But if it's at anything above 1, it's going to bend through and not go straight through. All right, let's take a look and see what happens here. Oh, I didn't talk about the end there. I'm sorry. I was just looking at the guided notes. I didn't talk about this last little statement. If I were to start by looking at the graph, and I gave you a graph that looks something like this. I've got this function that, I don't know, it bounces here, bends through, and then bounces. Well, let's pretend like that actually bounces over there. I see an even root here, an odd root here, and an even root there. Do I actually know what the multiplicities are? No. I just know their even or oddness. Okay, that's all that you really know. I know that first root on the far left side has to be at least 2. Could be 4, could be 6, could be 8. I don't know. Right? And I'm talking about the multiplicity, not the location. Maybe there's 4 roots there. Maybe there's 4 zeros there. I don't know. It could be 4. It could be 6. I don't know. This bend through. I know it's at least 3. It's not 1 because it would have just gone straight through the x-axis. I know it's at least 3. Could be 5. Could be 7. Could be 9. I don't know that from just looking at the graph. Again, same thing with the bouncing off here. It's even. I don't know whether it's 2, 4, 6. I don't know. But I know it's at least even. Okay. Let's take a look here. Identify the roots of the equation and state the multiplicity of each root. Multiplicities are going to be key when we start making connections between the degree and the number of roots that we have. All right, now, the only thing that we know how to do right now is to try to factor it down, and if it doesn't factor it down, then we have to use our graphing calculator. So let's first start off by trying to factor it down. Let's see, because this is a 4 term and it doesn't have a GCF, let's see if this factors by grouping. Guess what? Does this factor by grouping? Bummer, dude. Sorry, that's a Sadie comment. She says bummer dude a lot. Sorry, I've kind of picked that up from her. So it does not factor. So what you have to do is go to your calculator and see, okay, if it doesn't factor, I've got to figure out the points where it crosses that x-axis. X to the third, 6x squared, 12x, oops, minus plus 8. Zoom 6 this. Oh, well, now zoom 6. All right. What do you notice about the graph here? What does it look like it's doing? Looks like it's bending through. It looks like it's bending through. Where does it look like it's bending through? I hope it's at -2. That'd be really nice. How do we check to see if it's actually at -2? Synthetic division. Let's do that. Let's run -2 through. 1, 6, 12, and 8. 1, 4, 4, 0. Did it actually happen at -2? Yep. How do I know that? The remainder was 0. Okay, so remember that root corresponds to this factor, left with an x squared plus 4x plus 4. And I just got that x squared plus 4x plus 4 from the bottom of the synthetic division. Okay. Can that factor? Can this quadratic factor? Yeah. It can factor into an x plus 2, x plus 2. Factors of 4 that add to get to 4 are 2 to 2. All right. So that means that all of my zeros, that's the goal here, right? Identify the roots of the equation. X equals -2. And then I want to state the multiplicity. What is the multiplicity? 3. With a multiplicity of 3. Which only confirms the fact that, yes, it did indeed bend through at -2. Let's do one more of those. There we go. All right, I got 2x to the 5th plus 16x to the 4th plus 36x to the 3rd minus 54x. All right. First thing that I'm going to do is try to factor it. Is there any GCF? A 2x. Let's pull it out. Leaving us with an x to the 4th plus 8, x to the 3rd plus 18, x squared minus 27. Now at this point, I might try to factor by grouping in the middle, but guess what? It's not gonna work. Spoiler alert. All right, so what do we do now? Well, to try to reduce it down, that thing's gonna go in our calculator. Yeah, you keep chipping away and you go with the piece that's not factorable into your calculator. So let's see what happens here. We got, clear that out, we got an x to the fourth plus 8x cubed plus 18x squared minus 27. Fourth, 8x squared, x cubed, 18x squared minus 27. Graph. Okay, it looks like here, it looks like it bends through. You know, I saw it in like kind of the animation of it. It slowed down and then sped up again after this. Looks like it bent through there and it went straight through right there. Okay, so I've got two options. Which option do you want to go with to synthetically divide? 1 or -1, -2, -3? Let's try 1. 1's an easier number to multiply with. So let's do it. So we put 1 in the box. I keep chipping away at this red piece. 1, 8, 18. Don't forget to catch the 0, -27. Keep going. 1, 1, 9, 9, 27, 27, 27, 27, 0. All right. So I had my 2x that I originally pulled out. I've got this corresponding factor of an x minus 1 that I just removed. And now I'm left with an x to the third. What the heck was that? X to the third plus 9x squared plus 27x plus 27. Can I factor that x to the third plus 9x squared plus 27x plus 27? No. I could try to factor by grouping again, but again, spoiler alert, doesn't work. Okay, well, what else can I do now? But I had some roots that I could possibly have used again, right? What's the least amount of multiplicity that this -3 has? 3. It's got to be at least a 3, right? I could do synthetic division with this 3 times, and then I would exhaust the -3. So let's run negative. That's really annoying. -3 through this. So 1, -3, 6, -18, 9, -27. Synthetic division is fun, isn't it? Just like it. Just looks orderly and neat. So we got a 2x, an x minus 1, this corresponding factor of an x plus 3, and then an x squared plus 6x plus 9, and that factors. Okay, so what does that tell us? That tells us we've got a root at x equals 0 because of the 2x. We've got a root at x equals 1 because of the x minus 1. And then we've got a triple root at x equals -3. So the multiplicity here is 1. The multiplicity here is 3. And that's truly my answer. From the 2x, you would have set this equal to 0. Sorry, I know I kind of like rushed the ending there. Bell's got to ring. We're not doing anything new tomorrow, just doing more examples tomorrow. Okay, just a couple of problems that we can do with this. We'll do more of this stuff. This last problem, we'll do definitely more of that stuff. So don't worry about that. We'll do that tomorrow. That's Wednesday, then Thursday again, kind of treading water day, where we'll just, review section 6.4 and 6.5. Okay, I'm going to stop the video real quick.